Okay, just now we discussed how to really solve the constant coefficient in the ODE. So it just only takes 3 steps to find the homogeneous solution and find the particular solution, and also find the complete solution by adding them. So first, let us consider how to solve the homogeneous equation or the homogeneous solution. So suppose we have a nth order constant coefficient ODE, and for simplicity we consider a second order equation here. We only consider a second order equation here, which is like we have ABC, and then A multiplied by the second derivative of X, B multiplied by the first derivative, and C multiplied by the X, and then equals 0. Because for homogeneous equation, we just let the right hand side to be 0. And then we try to solve this one first. So we try to assume x of t is an exponential function, e to the s of t. You may ask why we need to make this assumption, and I would say it works. And probably you can remember it because this is actually related to the Laplace transform or the Fourier transform. So and you can simply imagine that we have a function here. We need to take the derivative, and you know that when you take derivative of the exponential function, it will be nothing but itself and then multiply by s for the first derivative, because you need the chain rule. It is like if you have d dt exponential to st. So exponential to exponential to st, something like this. So it should be like exponential to st, and then chain rule, you need to take the derivative to the exponent. So it is like d dt st. So it is like s times exponential to st. So you have the original function itself, as well as this s. This s will be useful, so we can just put it here. So for the second derivative, we have s squared exponential to st. For the first derivative, we have s times exponential to st. Of course, this is the original equation. So as long as exponential to st shouldn't be 0 for any value, exponential can be 0. It can approach 0 if the exponent is minus infinity. Then this is approaching 0, but it is not 0 at all. So exponential to st can be cancelled. So here we will have a second order algebraic equation, which is like ax squared plus bx plus c, but here we have s, actually the same. So here we will call it the auxiliary equation, or the characteristic equation. For this one. So when you look at this one and this one, so we have second derivative, so it turns to s squared. First derivative turn to s. Original function turn to be a 1. So we have a s squared plus b s plus c equals 0. So it turns to this one. Okay, so the next step is to solve this one, and and of course you should know how to solve this, because you learned this one in junior school. So, and of course you know for this second order algebraic equation, there are 3 cases for the for the delta. So we know that b squared minus 4ac is called the delta, and if delta is larger than 0, there will be two distinct real roots. And if delta equals 0, then we will have repeated real roots. And if delta is smaller than 0, then there will be complex conjugate roots like a alpha plus or minus I beta, plus or minus I beta. So yeah, so we know for the first case we have distinct real roots. And in this case, the homogeneous solution or the complementary solution. So yeah, actually for the homogeneous solution, we also have another name called the complementary solution. Different both will have different names, but it doesn't really matter. So we have xc to be this one. You may ask why, because here we have x of t. We have x of t satisfying a x double prime plus bx prime plus c equals 0. Cx. Something like this. And after solving this one, we get the roots to be s1, s2, which means that x1t equals exponential to s1t is a solution to this one. And also x2t equals exponential to s2t should also be a solution to this one, to this equation. And as much as this is a linear equation, which means that we can also have a1x1t plus a2x2t to be the solution of this one, which is the general form. As much as a1 and a2 are arbitrary real number, then it will also satisfy this one. Because I just already mentioned that this is a linear function, which means that we have, as much as for this one it is like f of this one, f of x equals g of t. It is like f of x equals g of t. Now we have 0 on the right hand side for the homogeneous solution. And of course we have x1 to be the solution, and also we have x2 of t also be the solution, which means that this is 0 and also this is 0, and in this case this is also 0, right? No matter what I1 and A2 and A1 and A2 is, then the right hand side is 0, and we will find that this is also the solution. So that's why we have the complementary, we have the homogeneous solution or the complementary solution like this one. We have this root s1, s2, so we have exponential to s1t times a constant c1, and then plus c2 times exponential to s2t. As much as this is a solution, this is another solution. So here we call it the linear combination of these two solutions. It's also the solution to the original ODE. Any questions? Yeah. So next case is a little bit more complicated, which is the repeated root. If we have repeated root, we can't really get this one, because if we have because it is like we only have one function for this case, exponential to s1t, which is exactly the same as exponential to s1 s2t, because s1 and s2 are the same. So if we just write a1 x1t plus a2 x2t, which is nothing but a1 x1t, because these two functions are actually the same, so it is like a constant multiply this one only. Now we actually need to have this term. We need to multiply by t here, so that there are actually two functions. So actually you can just remember it as much as you have repeated real roots, then you know you not only multiply this answer by a constant, and you still need to add the first order term here. Or you can just imagine for example, if we have a constant coefficient ODE like x double prime plus 2x prime plus x equals 0, then we know that we have the auxiliary equation or the characteristic equation to be 2s s squared plus 2s plus 1 equals 0. Then we have s to be minus 1 minus 1, which is repeated real roots. So we know exponential to minus t, minus 1t, right? So we have, this is one of the solution. And we actually need to find another one. We know if you just believe this one is correct, then you should get the complementary solution to be c1 plus c2t times exponential to minus t. But how does it come from? We can actually let x to be g of t times exponential to minus t. Yeah, these functions probably will be useful, so we definitely will assume it multiplied by another function to see what this function is. Then if it is not a constant function, then this one is independent to this one, then we can just add them together. So let's try to substitute this one into here. So we have a x prime to be, by the product rule, we have g prime of t times exponential to minus t plus g of t times minus exponential to minus t, because we have chain rule, so we have a negative sign here, which is g prime of t exponential to minus t minus g of t exponential to minus t. So x double prime would be like g double prime of t exponential to minus t, and then minus 2 g prime of t exponential to minus t, and then plus g of t exponential to minus t, right? You need to take the derivative and then apply the product rule again, and then you will actually find this one to be the second derivative. So we can put in this one and this one back to here. So we will have g double prime of t exponential to minus t minus 2g prime of t exponential to minus t plus g of t exponential to minus t plus 2 times of this one, 2g prime t exponential to minus t minus 2g of t g of minus t plus x is this one, so plus g of t exponential to minus t equals 0. Okay, so we can see that this term and this term can be cancelled. This is g of t exponential to minus t, this is another one, this is minus 2, so this one and this 2 can be cancelled. So the remaining one is this one, which is like g double prime of t exponential to minus t equals 0. All the term cancel except this one. And actually this one cannot be 0, so we just discard it. So we have a g double prime of t is 0. So take the integration, we will have a g of t to be a constant, call it a c2. Call it c2. And then integrate it again. So we have a g of t equals c2t plus c1, which is actually a first order polynomial. And then if you take second derivative of it, it will of course be a 0, which means that g of t is this one. So we put it back here, so we will get the solution like this. So that's why we need to multiply a t here, because we have a second derivative to be 0. So this is the second case, which is still not too difficult, I think. So yeah, and the third case is if the delta is smaller than 0, we will have complex root. Of course, the alpha will be like minus b over 2a, and beta will be like square root of 4ac minus b squared, and then over 2a, something like this. So, but yeah, we assume that if this is smaller than 0, if this delta is smaller than 0, then it is a complex conjugate root, so we have alpha plus or minus I beta, and I is the square root of minus 1. And yeah, and the expression will be like exponential to alpha t times c1 cosine beta t plus c2 sine beta t. Yeah, so this is even more strange, maybe to you, but actually it is not that difficult, I think. So let's see how it will be like that. So now we know that x of t is like exponential to st, and now we know that s should be like alpha plus I beta, or alpha minus I beta. So the function should be like exponential to alpha plus I beta t, and it should be like exponential to alpha t plus I beta t. And yeah, as the exponent is a plus, so we can just make it like exponential to alpha t exponential to I beta t. So we already got this one. So how come the other one? So come the other term, which is the strangest part. So I will tell you that exponential to I beta t, exponential to I, maybe this one is more famous, which is like exponential to I theta is cosine theta plus I sine theta. This is called the Euler equation, Euler formula. Yeah, so actually if you have learned the Taylor series, Taylor series, you probably can prove this one to be correct, as much as you know exponential to x is 1 plus x squared over 2 factorial plus x to the third power over 3 factorial plus dot 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 dot. So this is the Taylor series expansion of the exponential function, or the Maclaurin series expansion of the exponential function. And also cosine x is 1 minus x squared over 2 factorial plus x to the 4th power over 4 factorial minus x to the 6th power over 6 factorial plus dot 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 up to the infinity. And sine x is like x minus x cubed over 3 factorial plus x to the 5th power over 5 factorial plus minus x to the 7th power over 7 factorial plus dot dot dot. I suppose you have learned it in the calculus class. If not, it is not difficult to prove it. Yeah, but yeah, I will not try to prove it here, but actually I suppose you have learned it. And yeah, so here you can just plug in I theta into here, substitute x by I theta to all this term, substitute x by I theta for all the terms, substitute I theta here for all the term. Then you will find it be like cosine x plus I sine cosine theta plus I sine theta will be exponential to I theta. So this is called the Euler's formula. So as much as we have this one, also another expression is like exponential to minus I theta will be cosine theta minus I sine theta, which is actually the same, but yeah, so actually they are dependent to each other, but yeah, both of them are useful. So here we know that we will have this one and also this one, which means we have two solutions. If we just follow the first case, then we can actually write xc of t to be c1 exponential to s1t plus c2 exponential to s2t, which is some sort of correct. And actually we have the first one to be this one. So it will be like this, and for the other one it will be like exponential to a alpha t exponential to minus I beta t, something like this. Which means that we can actually factor exponential to a alpha t out, and then we have c1 exponential to I beta t plus c2 exponential to minus I beta t. This like this. Now we can substitute this one to here and then this one to here. So we will have exponential to alpha t, and then it will be like a c1 cosine. Of course, here we have theta to be beta t, theta to be beta t, because we have exponential to I beta t. So we just substitute theta by beta t. So we have cosine beta t plus I sine beta t, and then plus c2 cosine beta t minus I sine beta t, like this. Actually we can just collecting the terms together, so we have c1 plus c2 cosine beta t, and then plus I C1 minus C2 sine beta t. And suppose we know that for the original functional for the original differential equation, it is actually real value function, which is real value function. So we will also suppose the solution will also be a real function rather than complex function. So we will expect this coefficient to be real. This is real. This is real. So that we should have C1 to be the complex conjugate of C2. And in that case, C1 plus C2 is a real number. And C1 minus C2 is a pure imaginary number. So multiplied by I will be a pure real number. In that case, we can actually rewrite it to be like exponential to alpha t, C1 maybe prime cosine beta t plus C2 prime sine beta t, like this. And here we don't write the prime here because we just don't want to mix up this C1 with this C1 prime with this C1, this C2 prime with this C2. So we have C1 prime, C2 prime here, but it is an arbitrary real number. So finally we can just write it as exponential to alpha t times C1 cosine beta t plus C2 sine beta t. So these are all the three cases of the homogeneous equation. Yeah. So no matter which case they are in, C1 and C2 are arbitrary constant, which should be determined by initial value later on. If we don't have the initial value, then all the C1, C2 will satisfy the original homogeneous equation. So up till now, any questions? Okay. So here are some examples. So for the first one, we have a 2x prime, 2x double prime minus 5x prime minus 3x equals 0. So the auxiliary equation will be nothing but 2s squared minus 5s minus 3 equals 0. And of course you can do some factorization. It is like 2, 1, 3, 1, and then you have minus here. So you have minus 5. You have minus 5. Minus 6 plus 1 minus 5. So you have 2s plus 1 s minus 3 to be 0, something like this. So you have s1 to be minus 1 over 2, s2 to be minus 3. And in this case, they are distinct real root, so the complementary solution will be C1 times exponential to minus t over 2, minus t over 2, minus 1/2 multiplied by t, which is a minus t over 2, and then plus C2 exponential 3t. So this is the first case. And then for the second case, if we have an equation like x double prime minus 10x prime plus 25x to be 0, then the auxiliary equation will be like s squared minus 10s plus 25 equals 0. And of course this is a complete square, which is s minus 5 quantity square. So we have s1, s2 to be 5. So in this case, we have 5 here, so we have exponential to 5t for this term, And of course, this is distinct real root. So we have C1 plus C2t. C1 plus C2t. And of course, if it is third order, like for example, if we have something like x cubed plus 3x double prime, maybe double prime. If we have plus 3x prime plus x to be 0. If we have an equation like this, we have s squared plus 3s squared plus 3s plus 1 to be 0. So s plus 1 cubed to be 0. So s to be minus 1 minus 1 minus 1. And in this case, xt will be like c1 plus c2t plus c3t squared exponential to minus t, something like this. So if we have triple repeated roots, then we have this polynomial up to the second order. If we have double repeated root, we have this polynomial to be first order. The first order polynomial will have 2 coefficients. The third order polynomial will have 3 coefficients. So we have 3 independent solutions. And then we have the linear combination to be the complete homogeneous solution. So this is the second case for the repeated roots. And then for the third case, if we have x double prime plus 4x plus 7 to be 0, then the auxiliary equation will be s squared plus 4s plus 7 to be 0. So in this case, you can just find the answer to be minus 2 plus square root of 3i, and then also minus 2 minus square root of 3i. You can use the equation like s to be 2a minus b plus or minus b squared over b squared minus 4ac, or you can do it by factorization. You can have s squared plus 4s plus 4 equals minus 3. So you have s plus 2 square equals minus 3. So you will have s plus 2 equals plus or minus square root of 3i, something like this. So you can get s1, s2. Yeah, as much as we have these 2 complex conjugate roots pair, so we have the homogeneous solution to this one to be exponential to minus 2t, because the real part is minus 2. So we have exponential to minus 2t, and then square root of 3 to be the imaginary coefficient. So we have cosine square root of 3t, sine square root of 3t, multiplied by c1 and c2 and add together for this term. So this is the complementary solution or the homogeneous solution for this equation. So up till now, any questions? Okay, so so here. So next part is to talk about how to find the particular solution. So for this part, you definitely need to remember something. Yeah, but actually it follows some logic like this case. When you get used to it, then probably you can remember all of this kind of solution. Then as much as you remember all this kind of solution, or you understand all this kind of complementary solution, you will see why we will assume the particular solution like that way. And yeah, so there are six type of function summarized here, which we will be able to assume the particular solution for this kind of function as g of t. So there are several top functions for g of t such that the particular solution is easy to be guessed. Guess means actually you need to remember the rules. So they are summarized as polynomials, exponential function, sinusoidal function. These are the three basic types. These are the three basic types, which means you will be facing this kind of ODE usually. Especially for the exponential function and the sinusoidal function. Or more specifically, the sinusoidal function is the most important case. Exponential function is still easy to guess, and polynomial not so. Not to be very frequently appear, because we will try to go to infinity as t goes to very large, so it will not be appear very often. And these three are the more advanced type. Actually, mathematically you know how to find the solution, but practically it will not appear very often. Maybe polynomial multiplied by exponential, maybe one will appear something like this one. It is like a polynomial multiplied by the exponential function. So other than this function, and analytical solution may not exist, or you may need to use some advanced mathematics like Fourier transform or Laplace transform to really solve it. Or of course you can use a numerical solution, use some computer software to solve it, or you can write some program using something like the finite difference to find the numerical solution. Okay, so let's talk about the first type. The first type, the particular solution for the polynomial is like, so it's like if g of t is a nth order polynomial, we denote it as p sub n of t. Of course, t is the independent variable, n specify the order of this polynomial. Then we can assume xp to also be an nth order polynomial. So let's see an example. So on the left hand side we have x double prime minus 2x prime minus 3x equals 4t minus 5. So this is g of t. This is g of t. And on the left side it is the function of the dependent variable. So the first step is to find the homogeneous solution, which means we just let the right hand side to be 0, so that we have x double prime minus 2x prime minus 3x to be 0, which is the homogeneous equation. And then from this one we can have s squared minus 2s minus 3 equals 0, and then we can find the roots to be minus 1 and 3 to be the solution for this auxiliary equation. So the complementary solution is c1 times exponential to minus t plus c2 times exponential to 3t. So in this case we can let our particular solution to be also be a nth order. This is first order, so we just let our particular solution to be a first order polynomial. which is like a plus bt, which is a first order polynomial of t. And then we substitute this term into the original equation. Substitute it into the original equation, which is 1. And so we have a plus bt double prime minus 2 a plus bt prime minus 3 a plus bt 3x equals 4t minus 5. So this is a first order function, and then double prime will be 0. And then if we have this one, we take the first order derivative. So this one will be b. This one will be b. And this one is itself. So we can, so we have minus 2b. Minus 2b is this one here. And then we have minus 3a, minus 3a, minus 3bt, minus 3bt equals to 4t minus 5. Now we can slightly collecting the terms. So on the left side we have minus 3bt to be here, and then minus 3a minus 2b to be here, and then equals 4t minus 5. And both of them are first order polynomial, which means that the coefficient, the corresponding coefficients should be equal to each other, which means that minus 3b should be the same as 4. So minus 3b equals 4. And then minus 3a minus 2b should be minus 5. So we have the other one. So here we have two unknown variables with two formulas, so that we can be able to solve a and b, like this one and this one. Which means the particular solution is a minus 23 over 9 plus minus 4 over 3t, which is this one. So finally we have xp and also xc. So the complete solution to this linear ODE is this one plus a plus bt, a plus bt, like this. This is a complete solution for this one. Okay, any questions?